Hello everyone. This is our first session for the Mongo certification course. In the first module, that means today's session, so we'll be exploring the introduction to MongoDB and what are the basic needs for exploring any of the NoSQL stores, what are the various types of our DBMS and NoSQL stores that we have, and where exactly does Mongo fit in, and what are the various classifications of the data stores and types of data that we can preserve, and what is the structure that Mongo actually comprises of, and a brief overview of the various kinds of activities or various kinds of stores that we can play around with. Starting with the first session, it's the introduction to Mongo Store. And the objectives that we have from this module, that means from this session, is we should be able to understand what are the various differences that are there. We're considering the various kinds of data stores that we have in place and how exactly they differ from each other and what makes sense in which scenario and what kind of store we actually preserve in there. And then understand the basic need for Mongo and the design of Mongo in itself. List the various set of tools that Mongo has, how to do the installation of Mongo on various environments, setting up MongoDB environment on a specific OS. What is the possible difference between a JSON and a BSON? Starting with the fundamentals, a database primarily, why exactly do we need a database, and how does a database look like, and what kind of advantages that a database give us? That's always a very important and challenging question that we should ask ourselves before actually choosing a data source or deciding that there's a need for data source. See, the first thing is when we're actually talking about large amount of data, that when we actually have high volume of data or large amount of data and there are possible connections in between the data that we have, we need to organize that, we need to manage that, and we need to ensure that there's a very high volume of reads and writes. That's where a data source or database actually comes in picture. That's something a database actually helps us out to solve that kind of problems or smoothen up our steps in there. And then giving us a well-defined platform wherein we can perform the data analysis with more convenience and ease. Or if we talk about giving a disciplined approach towards managing the data, keeping a more organized forms of data that we have in place. And then the most important is keeping fault tolerance in mind, and we're ensuring that we're able to handle security, we're able to restrict users from accessing various parts or various sections of data based on their roles and rights. We're able to devise various plans on the restrictions or on the various sections of a specific data source, and then recovering the data in case of failures or backup as well. So now if we talk about the introduction to database, there are various categories that a data source can actually be expected in, whether we talk about the AllTP or OLAP or the NoSQL. The NoSQL is primarily where Mongo actually be looking for. So then we can have probably there's Cassandra, there's Couch, there is React, there's Elasticsearch, it's so on and so go. Then in OLTP we have is primarily the RDBMS and more of real-time stores. So we have Oracle is probably one of the most popular backend stores. We have Postgre, MS SQL, MySQL, and so on and so on. And the OLAP, it's very specific, it's very peculiar with respect to the kind of data that we can store in OLAP, because it's primarily a DSS store. So you will not find many popular implementations in OLAP because OLTP is more popular, and most of the times you will see there are a lot of implementations of OLTP as compared to OLAP. For OLAP, that is and HANA are quite popular. So you can actually expect that you are actually storing data in a specific possibility or a specific nature. So what exactly an OLTP? If we talk about what exactly an OLTP is and what kind of information, what specifications does this store bring on board, that makes us choose an OLTP or an NoSQL or OLAP. So the OLAP is primarily for storing the real-time data. So the data that actually is just coming in as soon as the data is actually being pushed. The data is actually being sent in from the user, probably from somewhere from any of the possible locations. We just go and we push it there. So that's a primary reason where an AllTP will actually be is expected of more relevance. And since it's more of a transactional stores, so primarily when we talk about working in the banking and financial domains, whether we talk about the accounts, the managing balances, transactions, handling the transaction history, ensuring there's a commitment while we're transactioning, or in case of possible failures of one of the possible steps while actually executing a transaction. So you can make a decision while in there. And then since it mostly works on the real-time stores, so you can always expect the data is always pushed for a short-term storage, and then probably it's actually being moved on. Even though, I mean, it depends. It's not necessary that you will always have a short-term storage. There are data stores wherein we keep on pushing the data and we preserve it there for a very long time. However, it depends. It's conditional. But yes, both of the possibilities are quite observed in an AllTP store. However, in case of an OLAP, it's primarily based on the process data that we have. It's homogeneous in nature, so I mean it's standalone, so it's probably unique. So the type of the data that actually stores is very specific. Then the access to, we can always leverage OLAP when we're actually interacting with various DBMSs, considering that we don't have externals, we're not working with a transactional data source, we're not working with relations. That's where an OLTP will work. So certainly, since there is no concept of relationships, so the possibility of preserving a data is primarily long-term. So you will always have high volumes of data, and the duration of the lifetime of the data is primarily very long. In case of NoSQL is primarily, again, it's agnostic in nature, so because since it's schema-less, so it doesn't have any forms of structure. You can always store any form of unstructured source. It's regardless of what is the volume and what is the velocity of the data that you're actually pushing in here. However, in case of the transactional store, that's something we cannot primarily achieve in the NoSQLs, except for the graph data sources that actually help us with the ACID reflexes or the ACID principle. However, other than that, whether if we talk about Mongo on its whole or any other NoSQL stores that's column-based or document-based, those stores, they don't primarily look in for such specific stores. However, on the other hand, we talk about the volume of data can always be very high, so you can always expect that there will be the amount of data that's actually being preserved in the NoSQL stores can always be very long-term, and the expectations of data stores can be very unexpected because it's something that might be accessed at a very later point of time. Primarily, if we're talking about from an DBMS or a DBMS store, the SQL is a more conventional standard of actually specifying or executing the set of commands to process the data or to actually retrieve the data or to perform any specific set of operations on top of the data that we actually have in place in a DBMS or in a data source, whether that's AllTP or OLAP. So that's what the structured query language, or SQL as we call it, is being specified. So analyzing the data, we can have the analytic queries, we can define the structures of the data, the structure of a table, the structure of the database, the structure of the columns, how we're actually retrieving the data, how we actually specify the relationships, how we actually want to retrieve specific chunks of data, how we want to update or modify specific sections of tables. That's where SQL will actually help us out. Or then if we talk about the integration scripts, or if we talk about the administration or modernizing or monitoring tables or the data tables or the complete database on its whole, wherein SQL can come into picture. Or if we talk about performing various kinds of standardized operations, wherein we're actually looking in for processing any levels of database operations, whether we talk about the data definition operations or the DMLs, the data manipulation operations, changing the structure of the stores, so that's a database or a table, or actually modifying the data inside the tables. So in there, that's something where the SQL will actually come in picture. However, in case of a little more advanced flavors, less like a NoSQL. That's something wherein we actually really don't require SQL. So the major reason in there is that we actually don't have a conventional data source in place, so we don't have the relationships defined in there. And then we have a distributed architecture in place because the data is actually primarily distributed across multiple sections or across the globe, spread over different levels of nodes. That's something that's more common from a NoSQL store as compared to an SQL store, wherein there's always how the data is actually being preserved. And then primarily most of the NoSQLs are actually completely free of cost, and it's very simple to access their APIs. There is no concepts, it's unstructured, so it's completely agnostic of the schemas in place. Then the scalability is primarily, the horizontal scaling is relatively very easy and simple. That's what primarily the NoSQL is. Now, if we actually have a comparison of an SQL databases versus the NoSQL, SQL has been evolved, it's very stable, and it has been there for a very long time because it actually used to suffice majority of our expectations were sufficed within the SQL environment. However, considering the high volume of data and considering the stability of the systems that we have in the industry right now, so the problem is that with the intensity of the database, of the data interactions and the data operations that are actually happening around in the industry right now, so the volume of data that actually gets processed eventually is actually very high and it's very immense. That's why big data comes in picture now. In SQL, it's primarily we just have only SQL. It's a standard query language that you can use to perform operations on top of various DBMSs, even though there might be specific differences, slight deviations with respect to the specific database server or specific implementation. However, in case of NoSQLs, there is no specific type. There are multiple types. We have the column base, we have the key value, we have graph, we have document. So it depends on what kind of NoSQL store is that we are actually working with. So based on that, we can actually decide how exactly it looks like. Then if we talk about the SQL was developed, SQL has been evolving for almost 3 to 4 decades now. It's almost 4 decades now. More than 4 decades now. So somewhere around 1970s, when SQL actually came into existence. However, NoSQL is relatively new. It's almost less than a couple of decades, a decade or so. It's almost around the 2000s, the Y2K boom. So that's where NoSQL actually started to come into limelight. Even though actually, honestly, NoSQL actually started getting use of more realistic possibilities probably around 2003 or 2004. And that's somewhere around where NoSQL actually started making more sense to people who are actually working around with it. Obviously, for SQLs, we have a lot of implementation, and most of them are very popular because they've been in the industry for a very long time. We talk about Oracle, Microsoft's SQL Server, MySQL, Postgres, and so on. The list goes on and on. In case of, and most of them with SQLs, the challenge is majority of the SQLs are primarily paid for their license. Now, in SQLs, we always have a well-defined schema in place. That's something that doesn't get changed off. So once we actually have the schema, and that's something that we have to work out with, it's actually something that's actually a restriction in the SQLs. However, if we talk about the NoSQLs, they can always stretch. They're always very versatile in nature. So we can always modernize, or we can always change the structure of the stores in there. Because the advantage is that primarily the NoSQLs are unstructured in nature, and they don't actually abide by a standard schema. So we are not restricted or confined with whatever the schema actually looks like. So we can always change it. We can always change around with it. And that's a big advantage that we have in NoSQLs. On the other hand, if we talk about the scaling of SQL data sources, even though, it's possible, and that's actually something that we actually do quite frequently nowadays, considering because primarily we don't actually expect to be handling just a single instance. We always have multiple instances working together in collaboration to respond to a specific volume of data. However, the challenge is primarily vertical in nature. So, we can always scale up within that specific instance or not. The cluster management is not primarily one. It's not applicable to all of them. So there are a few sources that actually primarily don't support the distributed environment. They're not primarily distributed in nature. However, in case of NoSQLs are primarily distributed in nature. So the horizontal scaling is always very easy and makes sense in there as well, because the collaboration with the different instances and a well-defined cluster and a very organized data transformations are something that actually work, that get actually handled on the core of the NoSQLs. Or on top of, now if we talk about the dev models, we can always have the development models, we can have paid as well as then the support as well. It depends, I mean, what kind of instances we're actually working on. So based on that, the support can actually change as well. However, in case else, if we talk about NoSQLs are primarily open source. So the development is primarily open source, so it's not actually commercialized, except for a few, just like Neo4j. Neo4j is not all of the features are actually available in the community version. So there are a few features that are very specific to the enterprise version. So for that, not all of the code will be actually available openly. Then SQL is primarily for transactional stores. So the ACID principles are actually being implemented very strongly and stiffly. However, in case of NoSQL databases, it primarily works on base. Now we'll actually go through, I mean, how ACID works and how base works. ACID is a principle that actually stands on four major pillars: atomicity, consistency, isolation, and durability. The atomicity is primarily how a transaction actually being executed to ensure that the transaction has been executed successfully or not, or it's actually being executed partially. Let's suppose that we're actually executing an insert statement. However, we were actually updating the complete row due to somehow some of the reasons. As soon as we updated the first two fields, the transaction actually fell off, or we actually executed a couple of insert statements. The first one actually executed successfully, or the next one was not actually, it failed off. To just ensure that either both of the insert statements get executed successfully or none of them actually gets executed. So I mean, there's no possibility of acceptance of partial executions or partial failures of transactions, to ensure that there's atomicity in the actual transactions. That's what the atomicity principle actually talks about. The consistency is actually about the integrity constraints, or so ensure that that actually the integral components or the constraints are that are actually being managed within data sources. That's actually what comprises or that falls under the consistency, to ensure that the data is actually being maintained consistently, so that there is no failure of data, and if how the data is actually being read or how the data is actually being written to the database itself. That's what the consistency talks about. The isolation, it's more popular. For example, let's suppose that there are multiple transactions that are actually happening simultaneously within the same time frame, to ensure that they don't actually come in between, they don't come actually in each other's path, and they don't actually interact with each other. So every transaction is actually being handled separately. For example, let's take an example. Let's say that we were actually executing an insert statement into our table, and same insert statement, we're actually probably calling a delete statement at the same time, probably for a different table. And when we're actually doing the insert, we're actually getting the maximum number of rows that we have in here to actually increment the column ID for the unique identifier. For example, let's say there's a delete transaction that actually gets executed separately. However, due to any of the possible reasons, they actually know about each other and they actually communicate with each other in such a way that we're not really sure which of the two statements should get executed first and in which order. And then we're not really sure what is the last possible value. So there won't be any specific consistency in the values that we'll be expecting from the select max statement, for example, let's say. So in order to make sure that each of the transactions that are actually getting executed or that are getting processed on the database server are working regardless of each other, they don't actually really interact with each other, or they don't really depend, or they don't really modify the state of the other transaction that's actually getting executed. That's what isolation is about. The durability is to ensure that if we actually, for example, let's say that the data that we actually push into the stores, to push into a database, however, the data is actually yet to be written to the actual files of the database. So, I mean, the data is probably somewhere in between, probably in an in-memory or some temp memory before the actual process could get executed successfully. So due to any of the possible reasons, the data is still underlying. It has reached the database, but it has not been, the commit for the data source has not been executed successfully due to any of the possible reasons, to ensure that we don't actually lose that data. So to ensure that we have proper and viable durability of the data source that we are interacting with, that's what durability is about. To ensure that, let's suppose in such a scenario, due to any of the possible system failures that we can come across, that the data didn't actually get executed, didn't get processed, or didn't get executed successfully. So what happens is that we're not really able to execute the data successfully in there. So what we do is we wait for the system to actually come up again, and once the system is back up again, then the data actually gets processed successfully. That's what durability is. So these are the principles of the ACID, the atomicity of the data, what is the consistency, how integral the data is actually being maintained within the database, then the isolation, how multiple transactions are happening or they are getting handled in between, then the durability, how durable the data is. Now, if we talk about the base property from the NoSQL store, base is a little different than the assets. The base is primarily the basic availability, so how the data actually is available to actually being processed at a specific time, to ensure that the database is primarily available at most of the time. So there's always a high availability of this is not the high availability, this is the basic availability. So the data is primarily available up till most of the times. The soft state is to ensure that all the database stores should be consistent in writes at every possible time, because there is no proper atomicity in it's not a transactional system in nature by default for a NoSQL store, so it's probably differs. There's a possibility that at some point of time you might need to have a higher read consistency over writes, or vice versa. You might need to have higher write consistency over reads in some other scenarios. So it depends on what kind of operations we're talking about. Then the eventual consistency, to ensure that the data is always being responded consistently until a specific point, because it depends, I mean, how optimum the cluster is, how we have actually specified. There are a lot of factors involved in order to defend all of those base attributes in the real implementation side when we talk about from a NoSQL store, because NoSQL primarily it's dynamic in nature. Second, it primarily expects horizontal scaling. So unless we are not managed horizontal scaling and we're not defined horizontal scaling properly, so there's always possibility of failure in this state. Now, every NoSQL other than base works on the CAP theorem. So the CAP theorem says that every NoSQL store will not be actually able to defend, will not be able to support all of these three at the same point of time. So that means that there is no real-time possibility that a store will be consistent, it will be highly available, and it will be partition or fault tolerance at the same point of time. Now, if we talk about consistency, it ensures that the data is always consistent regardless of how many number of operations get performed on that data, or how many times the same operation is being performed. It's regardless of that. Or in case of the state change of data, or let's suppose that there was a modification in the data, and certainly, let's suppose if there were 5 different instances within a specific cluster of Mongo, per se. So now suddenly at one of the instances, the data actually got changed and it got circulated to one of the instances. And in the meantime, the same data is actually being retrieved probably from some other instance. And now to make sure that Now, since in this scenario, not the same data is not available on all the instances, it's actually available on one of the instances. This information is not being circulated across all the instances based on, how the data is actually being managed based on the sharding and partitioning principles in there. But now in this case, we need to ensure that the data is actually being pushed in there and it's consistent to make sure that all the nodes should get only the updated data. They should not expecting to return the older data or the historical data. That's what the consistency principle says. In case of availability, we ensure that in case of the data, how data is actually being sent across and it's being spread across multiple nodes in the cluster. So it's important that we ensure that data spread across these nodes is always available. So for example, let's say that we have 3 different nodes and one of the nodes actually goes down or is being shut down. Now the amount of data that was actually available on node 2, the amount of data should still be available if we execute the same query and we process it only on 2 nodes as compared to in the earlier possibility of executing the same query on 3 different nodes. At the same point of time, we should still be able to retrieve that data. We should still get the same copy of the data. So obviously that means that how the data is actually being balanced across the 3 different nodes and how the data is actually being managed again. So that's what the availability principle says. Now when we talk about the partition, is the system actually ensures that understand that within the cluster, we ensure that how we want to differentiate, how we want to segregate the data across multiple nodes based on which principle, and to make sure that once the data is actually being segregated with each other, then based on what principles different nodes will be able to communicate to each other to understand that this chunk or this section of the data is actually available with this specific node. That's what the partition tolerance is all about. So this is what the CAP theory actually talks about, to define the consistency, how the data actually looks like, what is the availability, how highly that cluster or how highly that data is actually available to the consumers, and how the data is actually being spread across multiple nodes, how the partitioning really works in what the CAP theorem is all about. There is a possibility, just like I told you, that not all CAPs, not all the NoSQL support can support all 3 of them at the same point of time. So there's a possibility that we can have a database that's consistent as well as available. Then there's a possibility that we can have the database as consistent and partition tolerant, or we can have availability and partition tolerance. So this is primarily that actually works, and then it actually differs from how that's actually, again, now which ones of them will be actually applicable to which database. It primarily depends on the kind of databases, because the consistency levels in Cassandra might be different, and they are actually different. So as compared to the consistency levels in Mongo, if we talk about, and the availability principles and the partitioning strategies across different NoSQL stores are completely different. Now, if we actually talk about the consistency and the availability, so it's primarily, that means there might be a single site cluster. So that means all the nodes are always available and they're always in touch. They might be always available in nature. However, if we talk about the consistency and the partitioning, that's primarily if we talk about that some parts of the data might be available. So there's a possibility that there might be some sections of the data that might be actually accessible or that might be available in some states. But the data is always retrieved. Whatever the data is actually being responded back with the number of instances that we have, it will always be consistent and accurate, because it supports the consistency and the partitioning principle. And now, if we talk about the availability and partitioning, it means that the system is primarily available in case of partitioning, or there's a possibility that we might have inaccuracy. There might be some inconsistency in the data that we had actually responded back with, or the data that we actually retrieved back. So there is a huge possibility around that area. Now, in the availability and consistency, that means primarily the SOAR DBMS, Neo4j, and Redis. For the consistency and partitioning, it's probably Mongo, HBase, Bigtable. The availability and partitioning, it's probably CouchDB, Apache Cassandra, React. The NoSQL databases, There are some bunch of features that a NoSQL database can actually have. The first is probably the structure of data. It can always support unstructured or even semi-structured. Even the semi-structured data formats are considered as unstructured, so we can call it as preserve managing the unstructured data. And then the concurrent transactions, or when we talk about the concurrent reads and writes. So the high volume of reads and writes is always it's actually a real-time possible expectation from a NoSQL store, and that's something that NoSQL actually can perform or actually can do with a bare minimum complexity or a concern. And then the response time, how much of time it actually gives the response back to the consumer who is actually trying to access a NoSQL store is very immense. And then with optimal high availability and reliability features in mind, so the downtime in NoSQL stores is almost nil most of the times, and that's actually how it should be. We should always have a nil amount of downtime that we are actually expecting for NoSQL stores to make sure that the availability of the cluster on its whole is very high and there's very little amount of downtime that's available in there. And then if we talk about changing the requirements with intensive updates, so the transition for updating the stores, updating the database, and the expectation for or the transition for actually modifying the changes or stuff, that's something that's very easy in a NoSQL store. Now, how exactly the database storage actually works in Oracle is primarily the OLAP or OLTP. If we talk about the transactions, so we can always store the data that's actually coming in from OLTP, or we can directly push in data from the DBMSs to a NoSQL or big data, or probably from the OLTPs, just like retail or ATMs. We can again directly push that to NoSQL stores. Now, the major advantages of NoSQL is with the V's that we have, the 4 or 5 V's that we have in NoSQL, that if it's volume, velocity, variability, or veracity. So for volume data, so what is the amount of data that's actually being pushed in, and the amount of data that has already been pushed into a NoSQL store, and how the data is actually being managed now. That would be when we are talking about the volume of data. That okay, probably today right now we have probably terabytes or exabytes of data that we have stored in NoSQL, and at which velocity that probably there is 10 megabytes of data that's actually being pushed in per second, or there's a higher volume of data that's actually being pushed into the data, probably as per the number of records that need to be pushed into a NoSQL store. Probably, let's suppose some 100,000 odd records need to be pushed in every second to the database. That's what the velocity is about. The variability is the various forms of data that we have in place. Since there's always a possibility that we can have, since it's unstructured, there's no specified possible structure that we can expect the data in. So there is always possibility that we can have data in various formats. We can have data probably in the form of movies. We can have data in the form of JSONs. We can have a music file. We can have a zip file. We can have a blob. We can have any forms of data that we can expect at the same time, even for the same source. That's variability. And then the veracity. So the veracity is probably the inconsistency or the uncertainty that can exist in the data that we're actually drawing, or the anomalies that we have in data, or there's some latency or delay in the data that we're actually getting. So there's not proper consistency in the data or accuracy in the data that we are actually getting. That's what the veracity is all about. So these are the basic 4 V's that we have in NoSQL. Now, other bigger advantages is that we can have various kinds of schemas. We can have a key value, we can have document, we can have column based, we can have a graph, and so on and so on. We can replace some of the possible use cases of an RDBMS with NoSQL stores, and even with graph we can actually replace almost most of the RDBMS stores with the NoSQL stores. with higher volume of data or higher volume of distributed data or distributed structures or distributed management of data, in there NoSQL actually makes a pretty good fit. And then the unstructured data are probably huge amount of data or bigger chunks of data and unpredictable or unexpected or undefined format or very new formats. That's something the data is actually being pushed in there as well. NoSQL makes more sense, and NoSQL can actually be very helpful in there as well. And then since we don't primarily have tables or we don't have a specific defined structure in NoSQL, so we can always play around how we actually want to traverse the data. The traversal of data or the transcription of data can always be changed based on our expectations. There's no one way of actually traversing or retrieving the data that we have in NoSQL. It actually ends up with a bigger advantage. It actually helps us off. Then the major advantages we can have is it's like agile in nature. We have it's similar to the NoSQL, right? It's unstructured. We don't really have a specific expectation in there. In the NoSQL stores, the various categories, or we have document based. In document based, so we have a singular key that is actually being linked to a specific complex data structure or probably nested level of data structures being uniquely identified or represented through a key, something similar to how Mongo actually preserves data. Then the key value formats, probably something like we have in Redis. So we have similar to a map. For every unique identifier, there's a value that is being stored. Then the graph store. The graph is primarily storing the data in the form of graphs. So there might be multiple trees who can actually define. So there might be well-defined relationships in between. So every node will be uniquely identified or represented with few set of attributes, and regardless of how its counterpart node will look like. So we can always preserve data on those nodes. That's what the graph is for. Then comes the wide column store. So wide column store is primarily wherein data is actually being stored in case on columns as compared to rows that we store data in conventional DBMS. Column-based structures are more optimal and more consistent in nature. Their performance is a little better as compared to graph or key value. Cassandra is one of the popular column-based stores, or we talk about Dynamo. Now, based on the kind of data that we have, that we are trying to preserve, and then the kind of reads and write operations that we'll be performing in the upcoming future, keeping that in mind, we should be able to understand that how exactly the data is actually being stored, how exactly the data will be preserved off, and which form of the NoSQL store I will be using. So there's a possibility that for few of the use cases, we might be going with document based, and for others, we might be going with key value. And in some cases, we might be going with graph or the column based. So it primarily depends on what is the expectation and need. Right, so types of NoSQL databases that we have in document, we have Mongo, we have Couch, and with Cloudant. These are the popular ones. In key value, we have Memcache, we have Current with Redis. Graph, we have the Oracle NoSQL stores, we have Orient, we have Neo4j. In column base, we have Bigtable, HBase, Cassandra, and a few of the commercial ones like the AWS's DynamoDB differ. Now, the selection, which ones to actually use and how exactly to define the implementation to make sure that this is the right fit for our storage and this really makes sense, and how exactly do we implement that. We primarily come up with three major steps that we have to keep in mind, based on which we can decide that this is the NoSQL store that we'll be going ahead with, and that's how exactly we can take a decision on that. We need to have the correct data model in place. We need to make sure that this is the kind of data that we'll be pushing in. Then we need to keep in mind of the pros and cons of the consistencies. What levels of consistencies we're looking for, or what is the expectation of consistencies? And then what are the basic features that we actually have in our DBMS when we're actually considering an NoSQL. So a lot of times, since most of our systems are already in place, so we need to keep in mind that there's a possibility that we might actually do a transition from an existing or our DBMS store to any of the new NoSQL stores. So to make sure that the transition is more simpler, so we need to make sure that there are a few of the features from the RDBMS side as well on the NoSQLs. Now, this is more on the generic on the NoSQL style. If we talk about how the brief about the Mongo and how exactly Mongo really looks like. Mongo is primarily, if we talk about, it's one of the most popular open source document-based systems, and it has a very impressive performance. Even though the performance actually keeps on going, it has a very consistent high availability, and it has a very extensively abrupt performance as well. It's scalable. It's very easy to scale Mongo up at any point of time. These scalability features in Mongo are relatively very simple and easy to take care of. In order to make sure that the NoSQLs, in order to make sure that the amount of processing times and the execution of more complex queries gets more simpler, that's where Mongo actually really fits in. Mongo is primarily, most of the data is being stored in the form of documents or the set of collections that we have. So it's primarily in the form of JSONs that preserve the data, even though to make the processing on the data a little more faster. Since it's an unstructured source, so the data you will not find across the concepts of the identity columns or the primary and foreign keys in here, even though we have the key that actually uniquely identifies the data that you're actually pushing into a specific document. Now, the basic features of Mongo primarily, you can store the JSON data modeling primarily with the dynamic schema, so we don't really need to the predefined static schemas in place. You can always go with the dynamic schemas. We can have with the aggregation frameworks, and we can interact with the native MapReduce Hadoop framework as well. We can do the secondary indexes, even the induced spatial queries as well. We have there's a lot of built-in features in Mongo for the replication and high availability. We can always do the auto scaling of the data, so the horizontal scaling and sharding, and how to do the partitioning of data across multiple nodes to ensure that the data is not being pushed consistently across one single node, and it's being balanced. All the nodes in the cluster are being balanced very accurately and very properly. That's one of the key features of Mongo. Then if we talk about there's a lot of community support that's available that actually makes Mongo very convenient to define these implementations, because a lot of the communication with Mongo is relatively very easy and simple. So there's a lot of community support available, and the drivers and APIs that are available in there that actually give us that actually make it a good fit to actually interact with using any of the application layer languages. The reasons, it's always an important thing. What are the reasons why we should actually make use of Mongo? Obviously, the scalability is a big factor. And then the streaming of the data. So, the development to enhance the development board or development life cycle. That's another big reason that Mongo actually becomes a good fit, because the retriable, for example, the retrying mechanism for writes to make the data more consistent and to ensure that we don't lose writes. Mongo has a retriable write, so to ensure that we have a more managed error handling, so we don't come across with too many errors in case of few of the writes actually missed off from the list. They are still being actually retried. They're still being considered for retry mechanisms. That's what the retry is. And then create different data pipelines to stream the data. And we can always change the stream of those data, how those streams will actually really look like when we're actually pushing data from Mongo to the outside world, all from different worlds to Mongo in itself. Then the shard awareness of the secondary reads to ensure that data consistency is there, as opposed to any of the possible reasons that the data that's actually available on the primary shard, due to any of the reasons that shard actually goes down off. And Now, since the shard has gone down, I have to make sure that we don't lose the data based on the replication factor that we have specified. Any of the secondary shards will come up and be elected to respond to the queries that were actually being sent to the primary shard, and then based on the geographic locations as well, that which one of the secondary shards is nearer. In case the secondary shard is the nearer one who's actually responding to the request, based on that we'll be able to execute or we'll be able to respond to that specific query or specific expectation of that query to ensure that there's consistency in the data that we're actually pushing on from different shards. Then if we talk about the manipulations or the processing in Mongo is quite easy as well. There are a lot of inbuilt functions or methods that actually smoothen off the process when we are dealing with the retrievals of data that in there. And we can always have the complex possible combinations when we're actually when we are talking about the manipulations of data or the updates while in the development phase. For the scaling up, certainly we can always scale up even with the simplest configurations. We can scale up even to a very high, probably even more than 10x, or it's relatively very easy. And then the management of the JSON structures, the internal structure of how Mongo actually really preserves the data using the JSON structures, it actually really makes very easy to scale up the system in nature. These are the primary reasons for Mongo if we're actually trying to use Mongo, whether we try to speed up the development or to enhance the scaling. Then if we talk about the run in anywhere, because Mongo is globally distributed, we can run Mongo as a service, majorly using through Atlas. Or if we are working with cloud, so we can always run Mongo as a cluster of nodes in the public cloud, and we can directly access it from anywhere. And the automatic scaling actually removes off the development operations overhead by actually provisioning the additional clusters whenever it's actually required. So we always have some additional clusters really need to go and have an explicit DevOps team or DevOps tools linked to that. For the insights, we can always have, if we talk about the aggregations on analytics, there are a lot of pipelines that we can enable off for analytics with very limited amount of explicit code that we require. Majority of the pipelines are itself very strong and flexible enough to handle majority of the operations. When we talk about the aggregations or analytics, Mongo, it actually provides a lot of business intelligence integrations. If we talk about the SQL BIs, the SAP objects, the Collections, Tableau, or any other popular BI tools, though primarily Tableau is more popular in there. The Mongo actually provides a good integration with R as well, or the native libraries as well. They can help us. Even with the native libraries, we can do some data mining and statistics and data analytics. There's a very good integration with R available for Mongo as well that we can use to get some more additional and incremental insights. As per the market trends that has actually really grown, the NoSQL market is actually assumed to grow up to almost $4 billion by 2020. As per the CAGR, 35% of growth from 2014 to 2020. Mongo is primarily one of the leading NoSQLs, that's no doubt, among the Fortune 500 or the Global 500. A lot of developers prefers or intend to use Mongo over the others different NoSQL stores because it's relatively very easy and simple to configure and use from. As you can see, the data storage and data processing, how it has actually really grown off from the NoSQL stores as compared to any other store. The popularity of Mongo, or if we talk about Elasticsearch, Postgres, a lot of these tools are very popular these days now. And Mongo actually has a lot of reliable and a very long list of very renowned and reliable customers who have actually been testing and who have been actually working up with Mongo extensively and experimenting and leveraging the best out of Mongo. and giving us the major insights and various possibilities wherein we actually really feel that Mongo actually makes sense, whether if we talk about Google or Facebook or SAP, and then we have a lot of other users as well. There's a long list, pretty long list, and it's actually growing with every passing moment. Sectors, I mean, primarily in which areas we primarily use Mongo in for. If we talk about the service, surveillance data aggregations, crime data management and analytics, citizen engagement platform, program data and healthcare record management, or risk analytics and reporting, time series data, portfolio management and order capture, reference data, and market data management. These are some popular sectors, the hard sectors for Mongo implementations, or if we talk about the content management and delivery, user data and digital asset management, mobile and social apps, content archiving, 360-degree patient view, lab data management and analytics, that's the healthcare side, mobile apps for doctors and nurses, the e-commerce side. If we talk about the customer data management, real-time price optimizations, rich product catalogs, new services and digital coupons. Then in the AI and the M2M or the IoT side, the customer cloud and product catalog, the customer service improvement, machine-to-machine platform, real-time network analysis and optimizations. The advantages of using Mongo, it's very easy to scale. It can scale up very easily. It's document-based, so its schema is primarily agnostic in nature, so we can always have different structures of schema. Mongo supports a lot of dynamic queries on top of documents that it have. It doesn't really require any complex joins or intersections to retrieve the data. Structure is primarily, the basic structure is a JSON or an object in nature. The accessing of data is relatively very fast, primarily by using the internal memory in here. If we actually try to retrieve the data, and that's within Mongo, and the performance tuning and the optimizations within Mongo are relatively quite easy. We can easily do the configurations. There are very, very simple set of configuration steps that we need to perform in order to achieve those. Conversion and or mapping of the actual objects to database objects is actually really not required, since primarily we can actually always push the data into Mongo primarily through the application layer, so we can directly push that data without actually making a change on, or without actually really making a conversion to the data in there. Now, the standard terminology is and some commonly accessible or commonly supposedly using tools that exist in Mongo. By default, it's always a database. The database is primarily a group of collections, and collection is primarily, the database is primarily just a major high-level container where there can be various sets of collections, and each database primarily will have its own set of files that get actually created on the background in the file system on the disk. Obviously, a single server can have different databases. We can have more than one database in nature. MongoDB is the primary source for the Mongo database system. It's the initial source that is actually in there. And then for actually handling the data requests, we have the managed formats. We can have the background management operations as well. We can handle the various requests, the formats, whatever expectations we have. The collection. Now in the database, then inside the database, we can have collections. Collections is primarily a group of similar or related different documents that can be preserved inside a single database. Even though collection doesn't primarily impose or enforce a specific schema or style or pattern of storage structure in nature. So there can be different documents with different set of fields, regardless of how they look in nature. The only difference is that they might be primarily alike, or they might be related to each other. That's where primarily where the documents will actually make more sense. So, I mean, if we try to make a comparison from an RDBMS perspective to a Mongo, a database in RDBMS is similar, identical to a database in Mongo. Table in RDBMS is primarily identical to a Mongo collection. And the row, the actual record row in the RDBMS table is similar to a document. The columns that we have in RDBMS are similar to fields. The table joins, I mean, they are similar to embedded documents. So what we can have a nested documents. We can have a document object within another document object, the one that actually links to each other. That's what the documents are actually linked on. So because there's a possibility that we can have different kinds of documents, since we don't have a realistic relationship. There's no possibility of actually tying different documents together. That's where the embedded documents really make sense. The primary key in case of an RDBMS, we don't really have the concept of primary key in Mongo. Even can servers do MySQL, for example, Oracle. In Mongo, it's primarily the MongoDB. And then the actual commands in RDBMS, we primarily have the MySQL and the So that's it. So, I mean, from an RDBMS perspective to a Mongo, we have the corresponding from a database. With respect to RDBMS, we have a database in Mongo. With respect to a table, we have a collection in here. In comparison to a row, we have a document in here. With respect to the column, we have a field in here. With respect to various dependent tables or the join tables in RDBMS, we have embedded documents in here. In case when we talk about the server and client, the server is primarily the MySQL or the Oracle. We just simply run the Oracle in case of RDBMSs. In Mongo, it's MongoDB. MongoDB actually runs the daemon thread for executing the default server in there, and Mongo runs the clients. However, in case of, as compared to the RDBMSs, Mongo doesn't primarily really actually have the concept of primary keys. However, we have the key ID that is very identical to the primary key in RDBMS. So that's where these are some standard terminology with respect to the RDBMS and Mongo. Now, with respect to the tools, there are various set of tools that we have, and these tools actually are very useful when we're actually working with Mongo. They help us in various sections or in various different steps. In the core processes, the primary tools are primarily MongoDB, MongoS, and Mongo. They are primarily the tools that we actually have in there. Then in case of data export, import and export, we have Mongo import. We primarily have Mongo export for pushing the data out of the Mongo instance to. So the import and export primarily makes sense if you're actually trying to take a backup or restore from a backup. The diagnostics tools, the Mongo stats, the Mongo ops, the sniff, or the performance. So they are primarily used for the monitoring and the performance tuning to actually get a health check of the instances and to understand how the instances really look like. That's what primarily these instances or these tools will actually help us out in. All right, so the Windows services, we primarily have the MongoDB. This is the actual service, and the MongoS. These are the background services. Then for the binary imports and exports, they're a little faster than the data imports and exports. So we can take the Mongo dump, the restore, the bstore and dump, the Mongoose blog, or the Mongo files. That's the grid files. The introduction to JSON and the BSON. The JSON is primarily the JavaScript object notations. I'm sure most of you will be already acquainted with JSON. It's a very popular term everywhere whenever we are doing the transactions, when we're actually pushing the data in the form of request or response, whether we are preserving data. It's a very popular structure of storing data. Certainly, it's very lightweight. So the transmission of JSON is very convenient and clear. It's the syntax for the storing and exchanging is relatively very simple. It's primarily based on the JavaScript standards. So they have been implemented with most of the languages. that are around there. So if we talk about the web services, the communication on web services, if we talk about primarily just simply in the form of JavaScript itself, wherein the browser is, since most of the browsers actually support JavaScript and or they are actually being written on top of to execute JavaScript properly, that's why JSON is very popular. It's primarily used for sending communication from web servers to the app in between servers and web applications to make the transmission a little lighter and faster in nature. That's what primarily JSON is actually really looks like. So it doesn't really matter how exactly we're sending because it's a standard format. It's regardless of the language in itself. Well, on the other hand, the BSON is primarily the binary form of the JSON. It is just the encoded serialization of the simple JSON documents. So that means the actual JSON documents that we have in place, we just do the encoding for them in the binary format for the faster processing, since they are binary in nature. So they support the embedding of documents and arrays within others documents and arrays to make it more optimal and to understand, to ensure the complexity of the embedded documents that we have in Mongo. Since primarily all the data that actually Mongo stores is actually being written in the form of binary JSON. So to ensure that we support the embedded documents, so we can always have extensions, the flavors that are not actually available in the types that are really not available in JSON in itself, or some extensions, some probably it's being extended from some other source. That's something that we can actually add in the BSON as well. BSON is primarily, it's more efficient in BSON as compared to simpler JSONs, and the traversals to ensure, and the lightweight. It's very lightweight, since the overhead for any database presentations is primarily to ensure that there's a lot of overhead when we are actually doing the transmission over the networks, to ensure that the processing speed while we're actually sending the data for the transmission is very light and it's very fast. And that's what the major characteristics to ensure that BSON is very lightweight, since it doesn't actually send much of the configurations because it's conventionally similar to the JSONs that we're actually sending off. And the traversals, it helps us in actually smooth traversals when we're actually doing the searching a specific document within the list of various documents that we actually have in place. The BSONs can really help us out in a little faster speed. The traversals are really very easy in binary JSONs. Efficiency of actually the encoding and decoding of BSONs are primarily very, very easy, and it takes very little amount of time. And it's obviously because most of the Mongo is actually being written in C or C++. So, and as we know that the C and C++ always give us a very efficient performance in nature. So it's always very easy to make sure that BSON is very efficient in actually doing the conversions, whether we talk about the encoding or the decoding. It's a simple example. I mean, how exactly this might be looking like. Just like we have a simple JSON in nature, this is actually how the BSON will primarily look like. This is a conventional structure. I mean, it's not necessarily this will always look like, it depends on various factors as well. Same applies. The licensing and installation, Mongo is primarily, it has obviously most of the data sources have multiple editions. They have the open source one, the free one, the MongoDB, and the commercial one, the enterprise MongoDB. It actually comes at enterprise one primarily comes in with some advanced on the security side and the management tools, and some additional integration APIs, ready-to-use integration APIs. These were something that are primarily not available in the open source flavors. Remaining other features, regardless of all the specific supports, I mean, just like we have the advanced security, management support, certified OS support, on-demand training, enterprise software integration, these are primarily inbuilt, plugged in, or shipped with the enterprise version. That's something, especially when we talk about the support, you don't get a commercial support in the community version, so that sometimes gets a little challenge. For the downloading, we can always download Mongo from the specified URL that we have that's mentioned in here. We can also download the NoSQL client. It's available in GitHub to have the UI representation for Mongo. Now we can download the MongoDB from the browser. So let's try to do that. These are the steps for the installation. On Windows, you download it from the browsers. Once you choose whichever installation you're actually looking for, then you can follow the wizard that's being mentioned in there. Once it's installed, then you can execute, you can start Mongo server, and you can access the data, go to the data folder, whatever folder you're actually looking for, run the Mongo servers, the MongoDB, and once it's 27017 in different command prompts, you can run the Mongo client and you can actually start accessing. Then you can probably download the NoSQL client if you want. So let's try to do that. Let me download MongoDB downloads. Say the download centers. So that's how you actually go to the download centers. See, there are various features. We have Atlas, we have database as a service, we have community servers, we have enterprise ops, and Compass. We go to the community one. We have, this is the installation, how we're actually trying to install. So we install, it downloads the GZ, right? So the GZ is actually getting downloaded now. Once it gets downloaded off, then we download the NoSQL client. Go to the NoSQL client. You can choose any of the clients that we have that are mentioned there. In the enterprise versions, they have various flavors that are actually available there, so you can choose any of those. So you download which NoSQL version you're actually looking for, right? The NoSQL client. Once you download the NoSQL client, run the Mongo client primarily, right? Once, if your Mongo is actually already installed, so it will automatically detect for that. So, or if it's not, then you can actually connect. Now, the Mongo is primarily actually looking for that specific object in there. So now let's say, right, so let's try to see if that's downloaded. It's still here. What we can do is we can install. So you can download any of the MongoDB GUI clients. So whichever actually suits you off, we can choose any of those. So let's see. So this is a NoSQL client. This is just to give the user interface to our client. So once you actually go through the wizard, you'll actually, since I am on, let me see. So in the download center, we have various options in here. We have the cloud one. Cloud one is for using Mongo as a service. Then the Atlas one, then that's what the Atlas is. For community, community one is primarily when we are talking about the free one. Then the enterprise one is the paid one, the ops managers, the complex. These are the connectors. All right, so we have Mongo in here. Let's go to terminal. Bin. All right, so it's saying there is no data file. All right, so easily access, we start Mongo with the super users with administrative privileges. Sometimes it's not actually able to access that. So it's starting now. Let's start the Mongo now. Let's go to downloads again. Downloads, Mongo. Executed sudo. Alright, so now we're actually logged in. What was there? So now, see the connection, we're actually already able to connect to the Mongo internal client. The OS actually gives the information about my OS. Now, that's exactly what we need to do. We're actually able, so that means the first step is we downloaded based on which machine that we are working on. Since I'm using a MacBook, so I downloaded my tar file. Then once I downloaded the tar file, I unzipped it. Then inside the bin folder, I executed from bin folder, I executed the MongoDB command to run it off. Once I started the servers using the sudo, that means the administrative privileges, then I started the Mongo instance, the Mongo client. And once I actually have the Mongo client in place, now I can run the Mongo specific commands in here. Okay, so let's see. Say show. Let me clear it off. Oh, DBs. Right, so this is the list of databases that we have in Mongo right now. So if I say use Edureka, it will. So what it does is when you actually specify, these are some standard commands that are very handy when we are working with Mongo. If we want to view the list of the DBs that we have in there, so we say show DBs, and then if we actually want to use a specific database, if the database does not exist, then we actually define that specific database within Mongo, or it actually points to that specific database if that database already exists. Now, if we actually use show DBs, right, so if I say use it to Edureka. Okay, so if you want to show DBs, if you want to show the databases, we say show databases or just show DBs. It will show the DBs in there. Say use admin, it will use admin. No, sorry. Say use Edureka, it will switch to Edureka. Well, that's something that we'll actually explore in next session, wherein we will actually be exploring more on the objects, what is there to, how we actually execute those commands, the various list of commands that we have in place, and how we actually modify them off, how we actually run those commands. That's something that we'll explore in our next upcoming session. And with that, wrapping up for this session. So thank you, Arn. And till then, have a nice time. Right, thanks.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!